Hello everyone, I am Vibhas Vats, presenting this paper on multi-view stereo algorithm called GC-MVSNet, authored by Vibhas Vats, Sripad Joshi, MD Reza, David Crandall, and Soon-heung Jung. A consistent scene requires geometrically consistent depth estimate across different views. The consistency is checked using cross-view projections. MVS algorithms takes two broader approaches with regard to geometric consistency. First is the repeated application of geometric constraints during the estimation process, mostly used in traditional MVS algorithms. Second is the geometric constraints applied as post-processing steps, mostly used in learning-based MVS algorithms. Our work, GC-MVSNet, is a learning-based MVS algorithm. Learning-based MVS algorithms typically uses CNNs to extract multi-level features. Using these features, it creates a matching 3D cost volume. This cost volume is then regularized using 3D CNNs to estimate the reference view depth maps. Once all the depth maps are generated, in a post-processing step, all these depth maps are fused together to generate a consistent scene point cloud, which looks something like this. Such methods use geometric constraints only in the post-processing step, which leads to a limited geometric cues during the learning process and requiring longer training time to learn to reason about geometry. GC-MVSNet explicitly models cross-view geometric constraints by penalizing geometrically inconsistent depth estimates during the learning process. With explicit modeling, the model should be able to develop a better understanding of geometry, thus improving on quantitative results, and quickly learn to reason about geometry, thus requiring fewer training iterations to achieve its optimal performance. To this end, we introduce GC module at the end of each stage to check cross-view geometric consistency of depth estimates and to penalize geometrically inconsistent estimates. Our model is a three-stage model: a coarse, intermediate, and refined stage. Each stage takes extracted features from the images as input and produce a depth map. This depth map acts as a new hypothesis plane for the next stage. The same depth maps are also penalized for geometrically inconsistent behavior at each stage. That is, at each stage, these depth maps are projected to the source views and then it is projected back. The back projected depth maps are then thresholded to collect the geometrically inconsistent pixels, which generates a per pixel penalty for each stage. And these per pixel penalty at each stage is then multiplied with the per pixel depth error at each stage to generate the relative depth values. These depth values, the stage depth values, are then combined to generate the final depth value. Cross-view geometric consistency checks uses forward-backward reprojection to check the consistency of reference view depth maps. This is a three-step process which includes projection, remap, and back projection. And the outcome of the back projection is used to select the inconsistent pixels for penalty. This is the algorithm that defines this process, the forward-backward reprojection. The projection step, it uses the estimated depth maps and project it to the source view. This is the step that defines the projection. It uses the intrinsic and the extrinsic parameters from the source and the reference views. Using the XY coordinate of this projection, the ground truth is remapped and then that ground truth is back projected using the extrinsic and the intrinsic parameters of the same source view and the reference views to the reference view, where we select the inconsistent pixels for penalty. This is the complete algorithm of the GC module. For each source view, we apply the forward-backward reprojection, which gives us two values, the pixel displacement error and the relative depth difference, on which we apply two different thresholds and select the inconsistent pixel in both the fields. We combine both the errors with logical OR and then assign each inconsistent value a 1 and all other value a value 0. This generates a geometrically inconsistent mask, which is the sum over all the M source views. Then we take average of that mask to generate the final penalty value. The final penalty value looks something like this, which has a lot of extra penalty on the out of scope pixels. We apply a reference view binary mask to restrict its scope to the required pixels, and that generates the final penalty mask. This is the complete architecture of the GC-MVSNet, which is a 3-step process. At the end, we apply this GC module, which is multi-view geometric consistency module, which takes depth maps from each stage, the source ground truth, and their corresponding camera parameters. It generates the penalty, which is then multiplied with the per pixel depth error to generate the loss values. These loss values are then summed together to generate the final loss value. For quantitative comparison, we test our model on 3 different datasets: DTU, blended MVS, and tanks and temples dataset. On DTU, we have 2 types of results. First is using a common hyperparameter for all scene, which is general accepted approach, and on which we produce best overall and best completeness values. Second is using the scene specific hyperparameters, which is followed by GBI-net, and we produce similar result as GBI-net. On blended MVS, which does the depth map to depth map comparison on 3 different metrics, we produce best results in all these metrics. It shows that our depth maps are more accurate and closer to the ground truth estimates. On tanks and temples, which does point cloud to point cloud comparison, we produce very competitive results on both intermediate as well as advanced sets. The GC module is designed in such a way that it can be inserted in any depth map based MVS methods, just like as is shown here. On any depth map based MVS method, we can just add it and then penalize for the geometrical inconsistency of the estimates. To demonstrate this, we choose 2 different networks, CAS-MVSNet and Trans-MVSNet. We apply GC module at the end of CAS-MVSNet and Trans-MVSNet and keep everything else same, and then train the network. After training, we see that we significantly improve the overall metric for both these models, and we also require a relatively less number of epochs to train the model to its optimal performance. In conclusion, GC-MVSNet explicitly models geometric constraints in end-to-end DL frameworks. It provides more geometric cues during the learning process. It achieves a better understanding of geometry, which is shown by improved quantitative results, and quick understanding of geometry, which is shown by requiring less training to reach its optimal performance. Thank you.